Okay, so we have started the recording. Now, it's necessary for me to resize my window. Okay. So yeah, we're up and running here. We're going to start with a few announcements. Let me just double check my checklist here. We do have the chat window ready, and I'm monitoring the chat window. The audio system looks good. Okay, all systems are go here. Yeah, let's start with a few announcements. The reading assignment is we're going to go up to page 226. Now, looking at the video, I'm a little concerned about the resolution. Typically, that means we have some slow internet, but it should clarify in a minute here. Okay. Yeah, so by Friday, we're going to go up to page 226. And remember, I have indicated several sections in chapter 5, which you can skim over because they will not be on the homework or the exams. Okay, so this is exciting. Page 226, that will take us into chapter 6, where we're going to do some fascinating advanced mathematics. Okay, quick remark here. Homework 0, I've posted the solutions. So they are in the Homework 0 folder, and all of this is on B Courses. All of our files are available under Files. So the solutions are available. This is for you to check your work and have a great learning experience to make sure everything's okay there, check your understanding. And again, discussion section is a wonderful opportunity to talk about these issues. We had a question. This is another item here, and I'm pointing to it with the pen. There was a question 2 days ago about the grading philosophy. As you know, in the spring semester, spring of 2020, we had a very special kind of philosophy towards the grading that we would not be grading on a curve. Traditionally, these courses are graded on a curve, and in particular, Physics 105 has the policy of awarding A's to 35% of the students. So the top 35% of students get A's. And what that means is that's the union of A pluses, A's, and A minuses. Okay. And then when we speak of B's, that's the union of the B pluses, B's, and B minuses. So 40% of the students get B's, etc. That's the traditional curve. Now, a couple of days ago, we had a question in the chat window regarding the policy for this summer. What are we going to do? What I did is I asked the vice chair of the physics department about this, and so he is consulting with a team of experts. You know, we have a committee that's responsible for upper division coursework. They are putting together a statement, and we are, eagerly awaiting this statement. So we'd like to know what's going to happen. You know, there are basically two choices. We can, there's a notion of mastery of concepts. So in that case, we dispense with the curve, and we look for mastery of concepts. And typically, if you master 90% of the concepts, then you get an A. The result is a much greater number of A's, typically, than we would with the curve. So we need some clarity on the grading philosophy, and the administrators have vowed to deliver a document. So we'll have some clarity soon about the grading policy for this summer. While we're on the subject, let's talk about Zoom proctoring. One thing that is new this summer is that instructors must make the decision if they're going to use Zoom proctoring. What does that mean? Well, during the exams, we could require students to have Zoom running so that we can watch students during the exams. And again, the official policy from the university is that each instructor makes that decision for each course. So for our course, my decision is we will not use Zoom proctoring. And the reason is some students get an exemption from Zoom proctoring because it causes test anxiety and other problems. And this is documented by mental health professionals. And then my opinion is if some students are exempt from Zoom proctoring, then all students should be exempt because everyone's going to be a little bit nervous if they're being watched via a camera. So yeah, we will not do Zoom proctoring. We will not have a camera pointed at you during the exams. So that much I can tell you. The remaining question is the curve, okay? Will we compute grades on a curve or will we use fixed percentages? And again, we have a team of experts working on this question and I will report back to you when they let me know. Okay, wonderful. That concludes the announcements. Now I would like to make a few remarks on the homework assignment. As you can see, homework 0, solutions are published. It's up to you if you would like to work on the problems for another day or two. Or you can look at the solutions now. What's important now is that you think ahead to homework 1 because homework 1 is now fully part of the course. It's a full-fledged homework assignment. And as you know, you will upload a PDF file on Sunday at the latest for homework 1. Okay, so homework 1 is part of your grade. So let's make some remarks about homework 1. Okay, I'm going to share the screen, and I have uploaded another. You know, there's a folder devoted to homework 1, and I have uploaded another helpful document. Again, it's an image. I'm going to click share. I'm going to click on this thing. Now, Zoom 5.1 is making life difficult for me, but I am going to click here. Okay, so I prepared this document and I uploaded it this morning. What's the purpose of this document? Well, we want to exercise, you know, one of the objectives of this homework problem is to exercise our skills with setting up problems in, often we'll be working in a 3-dimensional space. This problem rapidly reduces to a 2-dimensional space. You see in the lower left, we have a diagram with 2 axes. Now, what is that diagram? Again, we're talking about super eggs, and several decades ago, these were extremely popular. It was common to see very fine super eggs, perhaps brass or even bronze. We're talking really, really classy super eggs in people's living rooms, etc. Yeah, so you know we want to get kind of an appreciation for the finer things in life. And now I've got this humble kiwi, which I think is every bit as super as a bronze super egg. Here's this kiwi. And now why did I assemble this? Again, because we, throughout this course, we're going to use our skills in geometry, 2-dimensional geometry, 3-dimensional geometry, and understanding how to bring in the algebra and the calculus. How do we achieve this union? We want to bring our understanding of the 3-dimensional geometry together with our understanding of algebra and calculus. So in this homework problem, we are doing that. And in this image, you see that coming together. So what is this? Well, let me briefly, I think I can do this. Let me very carefully now, I'm going to attempt to not mess things up here. What if I click here and do this? Yeah. And now I'm going to roll the mouse wheel. I'm feeling pretty good about this. Now I'm going to roll the mouse wheel to zoom in. Yeah. I believe everything's clicking now. So this was the first diagram I posted in order to help you with the super eggs, which is a very challenging problem. We'll make some more remarks about the skills. The series expansion, you know, we talked about the binomial series recently. This is crucial. We're going to be doing series expansions throughout the course. Again, we're bringing together all these techniques here on this homework problem. This diagram shows you 1/4 of a super ellipse. And as you know, a super egg is produced as a surface of revolution of a super ellipse. So the super ellipse is similar to an ordinary ellipse, right? An ordinary ellipse, you have a quadratic polynomial in 2 coordinates. You may have some multiplicative constants, but at its heart, you have the sum of 2 squared terms equaling a constant. That's a traditional ellipse. Right? People have been studying these things for thousands, at least 2,000 years, probably more. I often like to share my views, and I think it's quite likely people studied ellipses much earlier. Perhaps the earliest recorded writings are a couple thousand years old, but it could be really ancient antiquity. People were pretty smart back then. Okay, this diagram shows you 1/4 of a super ellipse. The coordinate system here, we have a rho axis. We like to use this lowercase Greek rho, right? This is one of the 3 coordinates from a cylindrical coordinate system. This is a natural choice, okay? And z, the z-axis is the axis of symmetry of the super egg, okay? And in homework 1, we give you a formula for the super egg. It's very similar to a traditional ellipse. However, we just bump up the exponent, right? Rather than an exponent of 2, we're gonna be thinking of 2.5, also known as 5/2. Okay, this construction here in this picture, there are several crucial things here to understand the stability of the super egg, right? We must, as participants in Physics 105, we have to have a good understanding for stability. And this is a wonderful opportunity to, you know, join everyone out there in popular culture, all those people who love super eggs. Let's join them and be on the forefront of the understanding of the stability of the super egg. It's remarkable that these things will stand upright in this. You can give it a bump, no problem. It will continue to stand upright. And yeah, we want to understand the stability. So the construction here in this diagram, we have a point called rho naught comma z naught. That's this point here. I'm pointing with a mouse pointer. We construct a tangent. This line, which goes through that point, is a tangent to the curve. And now we'll invoke our knowledge of fundamental geometry. We identify another point. This point is on the tangent line. And I was very careful to show that this point is on the tangent line. And furthermore, it's the closest point to the origin. Now that immediately allows you to bring in some classical geometry. If this is the closest point to the origin, then we must necessarily have a right angle. At this location here, where I'm pointing with the mouse pointer, there's a right angle. This line, which comes from the origin to this point, must necessarily be perpendicular to the line that's tangent. So that's the construction. The first diagram that I posted to help you with this problem was this diagram here. Now let's appreciate why this diagram is useful for a stability analysis. And that's why I prepared the second diagram. Here's the second diagram. And what we have in the lower left is a copy of the diagram that we were looking at a moment ago. It's copied and it's rotated. It's not rotated through 90 degrees or any integer multiple of 90 degrees. It is rotated through a funny angle. The funny angle achieves a parallelism between this green line. In the Kiwi photograph, we have a green line telling you the axis of symmetry. Okay, now I just remembered my chat window. The chat window is not visible to me right now, so I will check it in a moment. But as you know, they kind of put a hurting on me with the 5.1 zoom. So I think that we're gonna just go with, if we have a good functioning system, let's go with that, and I'll get to the chat window in a moment. Okay, so this diagram shows you how to take the earlier diagram and bring it into the picture in the photograph. This shows you an actual super egg. It's tilted. We want to understand how much has the center of mass risen relative to the horizontal surface, which is the table. That's the crucial thing here, understanding the potential energy of the super egg. And you know from the physics 7 sequence and the physics 5 sequence that the crucial thing is the center of mass. If you're in a uniform gravitational field, and that's a big if you're in a uniform gravitational field, then you need only look at the center of mass. Doesn't matter if you rotate the super egg about its center of mass, you're not going to change its gravitational potential energy. So we've distilled this analysis down to the following question. Look at the center of mass and show that if you start with a super egg that's perfectly vertical, if you tilt it, then the center of mass rises. It rises a little bit. If the super egg is perfectly vertical, then the center of mass is at its lowest point. If you can show that, you've shown the super egg is stable. So this is the analysis. Again, the vertical, I included some background scenery there. You see houses and trees and stuff like that. This instantly triggers your brain to understand we've got a situation here on our home planet Earth, and we know which way gravity is pointing, right? It's pointing straight down. The screen here provides some nice grid lines. The gravitational vector is pointing straight down, and the screen is a helpful coordinate system there. Okay, yeah, so in summary, this diagram tells you how to integrate various things. We're bringing together our knowledge of the three-dimensional geometry and our knowledge of the algebra. The construction, now you see there's the point of contact. The super egg is in contact. There's a single point of contact where the super egg touches the horizontal surface. There's the point of contact. Notice the point of contact is to the left of the center of mass. That's crucial. As you tilt a super egg, the point of contact moves to the left. If you tilt the super egg to the left, the point of contact moves even further to the left than the center of mass. That means you have a restoring force, and that means you have stability. Yep, so super eggs are really cool, and yeah, wildly popular. Maybe we can launch a revival. I think that's secretly what I'm hoping for here. Okay, I'm gonna click stop share. We're going back to our usual. Okay, we're back. Here's the document camera. We're gonna resume our lecture. Okay, now I mentioned for this homework problem, one of the objectives is to really exercise our knowledge of series expansions. Okay, let's do a nice foray into this topic. Okay, we're going to consider the following mechanics problem. Okay, let's look at an example. This example will be a nice opportunity to test our understanding of series expansions. Series expansions are central to homework 1 and the whole rest of the course. We're going to constantly be doing series expansions. Okay, so let's go through an example of a series expansion, and at the same time, we'll make a connection with chapter 5, right? We know one of the themes of chapter 5 is looking at a simple harmonic oscillator and then bringing in certain additional terms that bring in some more physics. Okay, so that'll be another theme in this discussion. We know that in some sense, there are simple harmonic oscillators all around us. That's one of the messages in the chapter. The simple harmonic oscillator, in some sense, it's the most fundamental example of an equilibrium. Well, here, we're going to look at a different equilibrium. Okay, here we go. Okay, so in this problem, we're going to look at one-dimensional motion. I've drawn a single axis. We have the x-axis. This is our one-dimensional space, okay? For this problem, we do have some apparatus nearby. And let me show you the apparatus. Here's the diagrammatic skills that we're going to use. Okay, so what we have here, these are two concrete walls. And this is a diagrammatic technique that is often used. This cross-hatching kind of is to indicate that this is a very rigid surface. And what we have here is a point of attachment. Here's our origin, okay? And here's our particle, and there's a spring here. Okay, so there you have it. Again, I'm going to verbally state this is some wonderful apparatus. Now we've constructed this in the laboratory. We have this particle. The particle moves along the x-axis. It's a one-dimensional problem, and it's moving under the influence of the forces. There are two forces because you have these two springs. The vector sum of the two forces, you see the sum will be a force vector that's parallel to the x-axis. The particle remains on the x-axis. You could contemplate a more difficult problem where you kick this particle off of the x-axis. We're not doing that. We're talking about a particle which moves along the x-axis under the influence of these two springs. Okay, now let's talk about these springs here. All right, one of the themes of the chapter is the so-called Hooke's law force, where you have a restoring force that's proportional to your excursion away from an origin. Okay, so you have some equilibrium location. You contemplate a displacement away from the equilibrium. There's a restoring force, which as a vector is a negative multiplicative constant times your displacement vector. That's one of the themes here for the so-called Hooke's law. Now, a deeper understanding of springs requires us to introduce the notion of the rest length of the springs. So let's record that over here. Over here on the right, we'll make a few very general remarks about springs, okay? If you jump right into this formula for the Hooke's law, right, basically force equals minus a constant times displacement, then you kind of sweep under the rug some fundamental physics here, which is a spring has an equilibrium length, the so-called rest length, an actual spring, such as I have inside this pen. I can guarantee there's a spring because when I push the little mechanical mechanism, I'm pushing against, there's a spring in there. Any sort of real spring has a rest length. If you remove it from the apparatus, place it on a table, it has some non-zero length. It's really just a very ideal spring that has a zero equilibrium length. A real spring has some equilibrium length. So the rest length is the length of the spring when you remove it from the apparatus, place it on a horizontal table, just have it sit there. It's got some sort of length, okay? So the rest length, we'll call this L naught, okay? And in this picture, we're gonna assume that the rest length is equal to the distance from the concrete wall to the axis. So let's call this distance H. Okay. So for this problem, we're going to assume that the rest length is equal to H. We're going to see some very interesting things happen for this special state of affairs, that the rest length of both springs, that they're both equal to H. Okay, so again, you have this notion of the rest length. The energy in the spring, what you do is look at the length of the spring minus the rest length. Okay, so this is important. For a real spring with some sort of rest length, you must look at the excursion. You could either compress it or you could stretch it. Either way, you see we have an energy. This is the energy in the spring. And of course, the familiar 1/2 K times this rest length. Now, what we often do when we talk about simple harmonic oscillators, we think of an ideal spring that has zero rest length. You can see that's going to be hard to manufacture if you want to wind some stainless steel coil and have it be zero, right? You see that's an idealization. What you can do is say, well, I'm going to consider, stretching it much greater than the rest length, but again, real springs are not going to be happy if you do that. So yeah, we often talk about this idealization. Really, the ideal Hooke's law spring is an idealization where we set the rest length to zero. Okay, so for real springs, we have this rest length. There's the energy. Okay, now let's figure out, under this assumption, let's figure out the total the total spring energy here. So for our problem, right? So this rectangular box here contains some very general remarks about springs, and here's the energy, right? This is our U. We like to use U for energy. Okay, let's apply it to the problem. If you're at some location X, here's the particle at location X. What is the length of one of these springs? Okay, So we use Pythagoras here, the Pythagorean theorem. Okay, there's the Pythagorean theorem. So far, so good. And we've assumed that we have a very special state of affairs where L naught is equal to H. So we got the x squared. Okay, great. So let's solve this. You can see that L okay, so far so good. What's the total energy? Well, it's twice the contribution from one of the springs. That's going to cancel this half very nicely. So the energy is K times L minus L naught, the quantity squared. Let's plug right in. We're going to take this expression, plug it in here. We got a K. What we have is the square root of L naught squared. Oops, wait. We got a problem here, folks. I copied it wrong. Sorry. Yep, and I looked at the chat window. I see that we do have some, thank you for catching that. That was at 106. Yeah, yep. I'm glad we had this uproar. There was an uproar in the chat window, and I appreciate that. And I too realize there's a problem. So everyone, we're all on board. There's a problem right here. I copied this wrong. This is X. How am I going to fix this? I'm going to put the X. Well, there's no easy way. I'm going to put a huge monster X. That's supposed to be X squared. Yeah, sorry about that. Okay, thanks for catching that, everyone. And let's proceed with our wonderful calculations. So now we're going to put this correct formula here, plus the X squared minus L naught. Okay. So this is the potential energy of the particle as it moves to the left and right. When X is equal to 0, what happens when X is equal to 0? This cancels that perfectly. We have 0, okay? Now, we want to understand what's going to happen here for small excursions away from equilibrium. And we know how to approximate this, right? Let's use our skills here in approximating this. Okay, so what is this square root approximately equal to when X is much smaller than L naught? All right, let's think about this. So consider we really need to focus. Why is there no, we had another question. Why is there no 1/2? Because there are two springs. So 2 times K over 2 is equal to K. Yeah, great question. We do have a 1/2. Here's a 1/2, okay? But we have these two strings. Both of these springs contribute the same amount of energy. So 2 times K over 2 is equal to K. That's this K here. So let's indicate that with some pencil. Okay, great question. And that the K that you see here is actually 2 times K halves, which is K. Okay, great question. And I'm really trying to be good about watching the chat window. I try and look there as much as possible. Okay, so let's look at that square root. Again, we're using the skills that you'll need for homework 1. So we got the square root. All right, the crucial thing, as always, is this. You must look for algebraic transformations that will give you some occurrence of 1 plus a small quantity. Okay, we want to do something that gives us an occurrence of 1 plus, here we're going to factor out L naught. So this is L naught, and we have 1 plus X over L naught squared. Okay, great. Now let's see what we got here. Let's start approximating this. We know that this is equal to L naught. Okay, and now we got our binomial series. This is 1 plus something small. The whole thing is raised to the 1/2 power, so that's 1 plus 1/2 X over L naught plus dot, dot, dot. That is to say, I've written an equal sign here. This is equal. If you have the complete series, which we've indicated with the dots, then this is truly equal. Now the approximation we'll do here, we want to understand the leading behavior. So it's approximately, and here's our symbol for approximately equal to L naught times 1 plus 1/2 x over L naught squared. Okay, so you can see where this is going now. We plug it in here. Something wonderful happens. We have the cancellation. This 1 times L naught is going to be canceled off by this minus L naught here. And this thing inside the big parentheses here is an x squared. So this is equal to a constant. There's some multiplicative constant times x to the 4th. Okay, so there you have it. This is a simple mechanical system. You could build one of these. The restoring force, the potential energy is proportional to the 4th power of the excursion. This is not a simple harmonic oscillator. And as you know, interesting things happen. The period will depend on the amplitude. We know how to compute that based on homework 0. The restoring force is proportional to the cube of the excursion away from the equilibrium. So this is a neat example. You can actually build one of these things if you have a couple of identical springs and they have some sort of non-zero equilibrium length, which springs do have. All right, so yeah, fun problem and a nice opportunity to identify an oscillator. This is an oscillator that you could build. And okay, we got a question in the chat window. How do we know how many terms to keep in the expansion? Oh, that's a great question. How do we know how many terms to keep in expansion? So the short answer is typically we are interested in the leading non-trivial behavior, okay? So we want to capture the largest term. So let's write that here as a principle. Keep terms, right? Right, so we're going to, in this case, we could have kept going. As you know, there's another term here where we have this ratio, our small thing, raised to the next power. Okay, that would be the next term here with a certain prefactor, which you can get from the inside front cover of the book. So we typically want to keep enough terms so that we capture the first non-constant term. Okay, so this is a general kind of principle. What you can do is simply keep a whole bunch of terms and then look at where this is going. For our problem, we wanted to understand the dominant behavior. What's the dominant behavior for very small excursions? So there will be higher powers here, higher even powers. The exact expression for the potential energy, it can be written as a series. And what we've shown here is that the leading term is this x to the 4th. So for very small excursions, all you care about is the x to the 4th. For larger excursions, if you want to know the exact potential, right, we're going to bring in some more complicated behavior, but there will be some other even terms here. And you could grind them out here. But in answer to the question in the chat window there, in this case, we went up to this term here because we saw that there would be a cancellation. We do have this minus L naught, which cancels off this 1 times L naught. And so it's this first non-constant term in the series, which ends up inside these large parentheses and gives us the dominant behavior. Yeah, so that's an excellent question. How do we know how many terms to keep? The safe thing to do is keep a whole bunch of terms and convince yourself that you have captured the leading behavior. Now, this excellent question that was in the chat window, we're going to revisit that because we will be looking at some fascinating problems here where the fundamental structure, remember the fundamental structure is that you have 1 plus a small. Okay, so I've written that here. This is the fundamental structure that you strive for. And what we've done here, again, we did an algebraic transformation. So we were looking at 1 plus a small quantity. But we're going to see some very interesting problems in the course where this small quantity is, in fact, its own little algebraic expression, which has, in some cases, 2 terms. Okay. And what happens is we'll have some interesting problems where this small quantity, for example, when we compute the tides, right, the surface of the ocean, you know, every day there are 2 high tides, 2 low tides. We're going to compute that. We'll see there are problems where you have 1 plus a small quantity, and this small quantity has its own internal structure. It's the sum of 2 terms, one that's really small and one that's somewhat small. And then the question again, as in the chat window, how do we know how many terms to keep? Well, we'll see there are cases where we need to keep some additional terms so that we truly capture all of the, so we must ensure that we capture all of the leading terms. So in this case, it was x to the 4th, but we'll see cases where this small thing is a linear and a quadratic term. And then when you start squaring that, you generate more and more terms. So yeah, great question, and we'll revisit that. We'll see some interesting things later in the course. Okay, so again, the purpose here, we're exercising our knowledge of series expansions. That's going to be fundamental throughout the course. We want to be very fluent with these series expansions. And this was a nice example of an actual physical system you could build that has an equilibrium, and however, the equilibrium is not a simple harmonic oscillator. Okay, one of the themes of the chapter is that most equilibria are simple harmonic oscillators. Perhaps you're doing chemistry and you're looking at some molecule and you're thinking about the vibrational modes of the molecule. Typically, as you have a displacement away from an equilibrium, there's some restoring force that's proportional to your excursion away from equilibrium. However, there are special cases where it's not a Hooke's law force, and it's nice to see a mechanical example of that here. Okay, so let's revisit. We're going to go back to chapter 5. We have lots of fun physics there to do. Okay. Now we're going to remember what we're doing here. We started with the good old SHO. Okay. SHO, the simple harmonic oscillator. This was a case where you had a particle moving under the influence of an ideal Hooke's law force. There was no need to talk about the rest length of the spring. It was 0. In fact, let's record that here so we bring together. Okay, so notice what we've done. We've brought together some thoughts from different parts of the discussion now. So to say that you're talking about a simple harmonic oscillator is equivalent to saying L0 is equal to 0. The rest length of the spring is equal to 0. Okay, wonderful. It's good to make those connections. That's what we want to do. All right, so we know for the simple harmonic oscillator, we had a differential equation where you had the second derivative of position equaling a negative constant times the position. Then we added, right, so step 1 was simple harmonic oscillator. The next step was include some friction. Okay, and the next step, we're going to include another term. We're going to include a driving force. Okay, so you see there's this progression. We have a differential equation right here, and then we start bringing in more physics, and these are terms in the differential equation. Okay, so there's a hierarchy, there's a progression. As you know, this stuff was covered in Physics 7A and Physics 5A, so we won't be going through all the details here, but there will be some general remarks and some technicalities that we really want to focus on here. Okay, there's some fascinating stuff going on with problems where you have 2 different time scales. And we're going to see that here as we go through this progression. And some years ago, I mean, there are people who devote their careers to studying problems with 2 different time scales. There's a fast time scale and a slow time scale. For example, you may have a molecule and the vibrational modes, they're very fast, okay? And when we say fast, we must justify that term. Fast compared to what? you can't just say fast. You have to say relative to some other reference oscillation speed. Okay, so when we say fast, fast compared to the rotational modes. Okay, so if you're studying molecular physics, the vibrational modes have a higher frequency, and typically the rotational modes, especially, this kind of is a preamble for the quantum analysis of molecules. You'll be looking at vibrational modes, and obviously there's a quantization with angular momentum. Okay, so again, some years ago I went to a conference devoted to these problems. Okay, and they occur in solar system dynamics too, right? There are lots of really fun things going on, right? People devote their careers to studying the rings of Saturn. There's some fascinating physics there going on with, when you start looking closely at those rings, there are things happening on different time scales, okay? And the interactions, you have different physics effects at different time scales. So in this problem, as we go through chapter 5, we're gonna see some different time scales, right? For example, when you include the friction here, the second item here, we have a bolted list. And so I'm indicating with the pen, the second item with the friction. You have two different time scales. There's the oscillatory time scale. Let's draw a picture. There's the horizontal axis. There's an envelope, right? Let's draw that like so. I'm gonna try and do a good job. I have to rotate the paper. This gets us into the biomechanics of trying to make a good diagram. There you see I rotate so that the natural motion of my hand could do this. Here we got the x-axis. We're talking about x as a function of t. So there's the envelope, and here's a typical. Okay, now as you do this, you have to make sure that you don't scrunch them up, right, on the time axis. Okay, so this picture is for our second bulleted item. Let me indicate that like this. This diagram. Okay. So you see there are two different time scales. Okay, let's talk about what's going on with the two different time scales. There's a time scale for the decay, all right? And, I talked about the several years I spent at Lawrence Berkeley National Laboratory working with some of these experts on superconducting radio frequency cavities. So these are electromagnetic oscillators that are required for accelerator physics. We're talking about an oscillator constructed out of, there's a cavity, a radio frequency cavity. That means you have a container, you have vacuum inside the container. You've pumped out the air using extraordinary vacuum technology. And inside this chamber, you have electromagnetic oscillations. So this is an electromagnetic oscillator. And these can have extraordinary Q values. We're going to talk about the quality of oscillators. And we'll have a way to quantify the quality. These electromagnetic oscillators, if the inner surfaces are lined with superconducting materials, and they have to be cooled to a couple of degrees Kelvin. So niobium-3 tin, popular choice. And they were, conducting ongoing research into improving these oscillators. So these superconducting oscillators, one speaks of superconducting radio frequency technology. They achieve extraordinarily high quality factors. And so if you draw this picture, the one we drew here, this exponential decay will be extraordinarily slow. The mechanical analog would be, if you have a pendulum clock, think of looking at a pendulum clock on the wall. You have the pendulum swinging back and forth. If this pendulum is as good as one of these superconducting oscillators, then it will go for 400 years and only suffer a reduction in amplitude of a factor of 2. Okay, so you start the pendulum swinging, pendulum clock, you check back 400 years later, the amplitude will be half as great. Check back another 400 years, it's down by another factor of 2. That's a very, very efficient oscillator. You're losing a tiny fraction of energy every cycle, okay? That's an extraordinarily high Q. So we're going to investigate that. And again, there are two different time scales. there's a time scale here associated with the oscillation. So strictly speaking, this is not periodic motion, right? Because the cycles are not exactly the same. But the zero crossings are evenly spaced along the time axis, okay? So there is a certain time scale for the oscillatory behavior, all right? There's a time scale for the oscillatory behavior, and there's a time scale for the exponential decay. This is a problem with two different time scales, and that's a fascinating business to be in. All right, so let's again revisit the question of where did this come from? Oh, and before we do that, again, I want to emphasize some of the connections here. When we include the driving force, right, we have this hierarchy. We start with a simple harmonic oscillator, then we add some friction, we study that and solve it. And then we add the driving force, we study that and solve it. So this thing here, this is the driven damped oscillator, DDO. Okay, we started with the SHO. These are standard abbreviations. The simple harmonic oscillator, that was the SHO. When we add the driving force, and the other D here is for damping, right? I wrote friction. You can also say viscosity, etc. Here we're going to say there's some damping. So the driven damped oscillator. Later in the course, towards the end of the course, chapter 12, we're going to talk about the DDP. So I'll include that here as a parenthetical remark. DDP and now, this is fascinating. Okay, but I want to take this opportunity to put this in perspective. All right, so in chapter 5 here, this stuff is all chapter 5. Let's really emphasize, this is chapter 5. Okay, so what we're doing here, we're working on an understanding that this material in chapter 5 is important foundation material. Later in the course, we have the DDP, the damped driven pendulum. Okay, it's very similar to the damped driven oscillator, except you have a pendulum rather than an oscillator, and a pendulum has a nonlinear restoring force. You know, for a pendulum, right, you've been studying this, the pendulum has a restoring force where you have a trigonometric function, the sine of the angle. There's an angular excursion, and in the differential equation, you have the sine of that angle. So the crucial thing here is that you have a restoring force that is nonlinear. You have a driving force, you have dissipation, and you have a nonlinear restoring force. Okay, so in chapter 12, we're going to study this system where there's a driving force, there's some dissipation, and there's a nonlinear, right? It's a pendulum that has a nonlinear, and the result is chaos. So this is fascinating. This is one of the objectives of the course. This will be chapter 12. It's the last chapter we're going to cover. We covered chapter 13 before chapter 12. Chapter 12 is the last chapter we'll cover. Chapter 12 will not be on the final exam. It's not really good stuff for final exam material, and that's why we'll do that one last. But it's fascinating in terms of the physics, and there was a realization in recent decades that most systems are chaotic. So this is a nice example because it's a 1 degree of freedom. Again, you'll just have a single variable, single dynamical variable. We're solving for this pendulum, and it's a planar pendulum, so there's just one variable that tells you the position of the pendulum. Another chaotic system is the double pendulum without dissipation. Okay, that turns out to be chaotic, but that's a 2 degree of freedom system. So Taylor thought about it, and he decided to focus chapter 12 on this DDP, the damped driven pendulum. So again, the point here is we want to emphasize that chapter 5, you know, much of this material is a review of things you did in your first year physics course, but we want to now appreciate some of the mathematical details and also see how this relates to some of the more advanced concepts. So chapter 12 with the chaotic systems. Chaos is a very exciting field of research. We do have professors at UC Berkeley who research nonlinear dynamics. Right? Nonlinear dynamics, very fascinating stuff. Also over in the math department, people are interested in nonlinear dynamics. Okay, so yeah, we won't be going through the details. You will recall from your first year physics course that you get this envelope, right? There's an exponential decay, and there is the oscillatory behavior. Okay, so when we include the driving force, okay, so let's talk about this one now, the DDO. Okay, so our differential equation now, we started with a simple harmonic oscillator. We include some dissipation, right? We assume the frictional force is proportional to velocity. That's a crucial assumption. It's a little bit of an idealization, but it makes the math work out really nice. That's why people focus on that assumption. And then we're going to add a driving force. So we have this driving force. Okay, and I wish we were in our physics building. In room 72, we have all these lecture demonstrations, and we have some very nice apparatus where you actually have a traditional rotating dial. You can dial in whatever frequency you want for the driving force, and then watch what the oscillator does. So here's the driving force. In terms of one-dimensional motion, we don't put arrows. There's no need for an arrow because this F can be positive, negative, or zero. That's sufficient to capture any sort of vector behavior. So we do not need an arrow here. This is the force as a function of time. It's useful to write the prefactor as the mass times this lowercase f naught. That's looking ahead to the calculation that comes later. It will clean up nicely if we write the amplitude of the force as this product, and we're going for the cosine of omega t. Okay, the crucial thing to notice here is that this omega is the frequency chosen by the experimenter who applied the driving force. As you know, there are other timescales in the problem. If you have a square root of k over m, right, that was the so-called omega naught, right? So we have to be careful with the notation. This omega, and it's nice when we get that apparatus from room 72, there's literally a rotating dial. You can experiment with omega. You turn the dial, you get a different value of omega, and you can explore the resonance. We're going to see there's some resonant behavior here. You can explore the resonance by literally turning the dial and seeing how the system responds to different frequencies. Okay. So we don't have that apparatus here. Remarkably, there are some interesting experiments you can do even with some simple apparatus. Now, we have the document camera, and there's also the video of me. I don't know if you can see both of those, but I'll just verbally describe what I'm doing here. I have a pencil which I'm suspending, like so, to create an oscillator, okay? And then, well, maybe I'll do this on the document camera. If you suspend the pencil, actually it's better if you have a meter stick, it works much better. And then if you move your hand left and right very quickly, you'll see that the bottom, the so-called pendulum bob, it's 180 degrees out of phase with your driving force. So for high frequencies, we're going to see this. You have this 180 degree phase shift. When you're on resonance, there's a 90 degree phase shift. And again, this is stuff you can illustrate nicely if you have a meter stick. So let's go through the calculation now. Before we go through the details, I want to present a summary, right? The idea here is to avoid getting bogged down. There's some rather technical details with the mathematics. Before we do that, let's present an overview of the behavior of the system, right? The crucial thing now for the DDO, the damped, I'll scoot the paper down like so, the damped driven oscillator, the crucial thing is there's some initial transient behavior which dies away, and then there's the asymptotic solution, okay? Also called the long-term solution. So the long-term solution oops. Okay, so the long-term solution is an oscillatory solution. It has a frequency that's exactly equal to this omega here, the omega of the driving force, okay? The initial conditions have decayed away exponentially, and we have this long-term solution. So here's our long-term solution. Okay, so there's a very interesting phase shift. One of the first and most important things to remark here is that the long-term solution has the same omega as the driving force. And it's certainly not omega naught. Remember, we had this omega naught, which was the square root of k over m. So the asymptotic behavior, this long-term solution is also called the asymptotic behavior. Okay, so that's a reference to the word asymptote, right? If you're plotting, say you're plotting a hyperbola, you know that there's a straight line you can draw in the picture, and the curve asymptotically goes, approaches that straight line, and it never quite gets there, but the asymptotic behavior is to approach that straight line. The same is true for this exponential decay that we had in our upper diagram here. So these two dashed lines, which illustrate the envelope, asymptotically, they both go to 0. That's the asymptotic behavior. Okay, so for the damped driven oscillator, the long-term solution is has this structure. And the crucial thing to notice here is the initial conditions have decayed away. So the system had some initial conditions, perhaps at time equals 0, you had some non-zero velocity. It doesn't matter. The initial conditions, the initial position and the initial velocity, they decay away exponentially. The asymptotic behavior is this, where the amplitude A is not arbitrary. It's governed by a formula, and here's the formula. It's convenient to write down a formula for A squared. It's understood that A will be the positive square root of this. Okay, so this is a fun one. Notice we have the fourth power of frequencies here. The denominator is seconds to the minus 4. That's really cool. Okay, that's the amplitude, and there's a phase shift delta. So relative to the driving force, there's a phase shift. Okay, again, wonderful formula. Let's do a quick sanity check here. Remember, beta has dimensions of inverse seconds, omega has dimensions of inverse seconds. So yeah, this is completely sane. You know, if you're computing an arctangent, whatever's in there had better be dimensionless. Okay, and it certainly is. The numerator is seconds to the minus 2. The denominator is seconds to the minus 2. The ratio is a pure number. And so yes, you can take the arctangent of that pure number and get this phase shift. Okay, so that's what we want to do first is just describe the behavior before we dive into detailed, messy calculations. Let's describe the behavior. And this is the behavior. You have an oscillation. It's synchronized, right? They have the same frequency. It's synchronized with the driving force. There is a phase shift. And it's very important to understand that the amplitude of the oscillation is determined by these parameters here. It doesn't care about the initial conditions. You may have had a large or a small initial displacement away from the origin. Doesn't matter, it decayed out exponentially. We're looking at the long-term behavior, and also the initial velocity decayed out. For the general solution is the sum of this asymptotic solution plus the so-called homogeneous solution, the solution without the driving force. Okay, so that's our first observation. So let's look at this formula a little more closely. Let's do this. Okay. So here we want to visualize, suppose we were in the physics building and we had this wonderful apparatus that's available in room 72. And you do have a rotating dial. You can explore different frequencies. So this omega axis, 2 pi, obviously omega is radians per second. That's 2 pi times the familiar frequency in cycles per second, right? Typically, laboratory equipment is calibrated in cycles per second. Same for automotive. If you're driving a car, the tachometer is telling you about the rate of revolution of the engine. Of course, they use RPM, revolutions per minute, but nobody's going from, no car I've ever seen is talking about radians per minute. Anyways, yeah, laboratory equipment, this includes electronics, cycles per second. So you adjust the dial and you look at the response of the system, you wait for transient behavior to decay away. Again, there's some transient behavior, it decays away exponentially, and then the steady state. Another term here is that for this here, one speaks of the steady state. Okay. So the steady state behavior, after you adjust omega, you have to wait for any transient behavior to decay away. And then again, you'll see some sort of amplitude. So what does that look like? Well, it's useful for us to plot a squared. We're going to see it's convenient to think about a squared. And then we can read off what's happening here with our curve. Let's see if I can draw this. Okay. Notice when omega goes to 0, so you plug in 0 for omega, this second term is 0, but the denominator is not 0. Therefore, here in this picture, I did not go to 0. It goes to some finite value. All right, but the usual kind of, this is the generic behavior of a resonance. Okay. If the damping is small, then the peak is near omega naught. We're going to talk about a distinction. In general, there could be a shift, right? Let's talk about that one later. You can see that the situation is going to get rather complicated. If omega is equal to omega naught, let's think about what happens. If omega is equal to omega naught, you have zeroed out this term here because omega naught squared minus omega squared, that's 0, okay? So if your goal is to make this denominator as small as possible, that is to say you're looking for the largest possible value of the amplitude, then yeah, by choosing omega equal to omega naught, you've zeroed out this term. The other term is not 0, okay? So this is somewhat of a greedy approach, right? It's greedy in the sense that you're trying to zero out this term, and you can do that. Yeah, I see there's a comment in the chat window. Just a moment. So you can zero out this term. However, you will not achieve your goal of minimizing the denominator, right? Because over here you have this omega squared. So it turns out there's a shift. Okay, now let me look at the chat window. Just to clarify, the omega naught we're using is root k over. Yep, that's right. So the omega naught equals root k over m. Yep, so I wrote it up there. The omega naught is the root k over m. Yeah, that's a good point. So we're going to, it's the so-called natural frequency, right? So that's in the absence of friction and the driving force. Okay, so what I'm saying here is without, right, this could turn into an algebraic nightmare. If you want to compute the maximum, it could get rather messy, right? If you do the kind of most direct calculation, which would be to take this thing, compute the first derivative with respect to omega, set it equal to 0, you could find the maximum, but it would be rather messy. So here what we're doing is, rather than getting into messy calculations, looking at the structure, the numerator is a constant, F naught is a constant. So the numerator is a constant. Our search for the maximum of this resonance curve is fully equivalent, trying to minimize this denominator. And again, if you immediately seize upon this term and make it as small as possible, which is 0, you can make this first term 0. That's not going to get you the maximum because you see you could tweak omega squared here slightly and make this term smaller. And here you would have some growth in this term, but because it's omega naught squared minus omega squared, that thing's squared. You pay only a small price. So the upshot is we can see by staring at this denominator, if you think of first setting omega equal to omega naught, you get pretty close to the maximum, but then reduce omega a little bit. Okay, so there's a shift. Let's save that discussion of the shift for a little bit later. What people do here for clarity is they talk about the full width at half maximum. So the abbreviation here, full width, half max. Okay, so that's the full width at half maximum. Okay, and this is very popular. I mean, if you go to a conference, often you will see a researcher talking about the full width and half max. The reason people like it is it's very clear. What you do is you identify the maximum, okay? So there's a maximum value. Then you look at the half maximum. Oh, this is not my best effort at half the max. I think we should go, yep, there we go. Okay, so you see the construction. First, you identify the maximum. Then you identify 1/2 of the maximum. And then the full width, that means you go all the way across. So it's nice. The nice thing about the full width at half maximum, it's a very clear term. Because otherwise, people can be very sloppy about talking about the quote unquote width. What's the width of the feature? They can be very sloppy. Do they mean the distance from the center over to here? Right? When people speak of the width of a Gaussian, right, we'll have a separate discussion about Gaussian curves. This is not a Gaussian, right? You see there's no e to the minus excursion squared. But when people talk about Gaussians, they're always talking about the width of the standard deviation. And there can be some sloppiness there. You can easily lose a factor of 2, and sometimes that's critical. And there are stories in the archives about basically disasters that occurred because people were sloppy about these factors of 2. If they're in the exponent, it's extraordinarily critical. And the design of large, expensive machines has been compromised in some cases by being sloppier. So sometimes you have to be very clear about the notion of the width. So here we have great clarity. The half max, right? I drew a horizontal line across the picture at 1/2 the maximum. Let's be clear, this is a squared. If we had a plot of a as a function of omega, then the notion of half would be different. Okay, so we're going to work out these details, but what we want to appreciate right now is that we can define Q. Okay, we're going to see that the full width at half max right. Remember, what we're doing right now is presenting an overview of the fascinating results. Later, we'll grind out those results. That requires some effort. But the full width at half max, the distance from here to here. Okay. We're going to see this is roughly 2 beta. Okay. And then we can define this Q. This capital Q, it's called the Q factor. So when you talk about oscillators, people are very interested in the so-called Q factor of the oscillator. So Q is going to be the ratio of this central frequency to the full width at half max. Okay, so we got our Q here, omega naught over 2 beta. Okay, so there's our Q. So one thing we'll do in the homework, we're going to show there's an alternative form, but the purpose, first of all, is to appreciate that this Q relates directly to our visual, what's our overall visual kind of impression of this picture. There's a certain width of the feature. If the feature is narrow, then this full width at half max is smaller, and then Q is larger. Okay, so let the record show that if you have a narrow resonance curve, then you have a large Q. Okay, so in general, when you construct oscillators, narrow is a higher quality oscillator. That means you have less dissipation. Okay, so high Q is good. So large Q is good. And again, I want to, again, sing the praises of these researchers at Lawrence Berkeley National Laboratory. They're building electromagnetic oscillators using superconducting radio frequency cavities. All right, we're talking about electromagnetic oscillators. And they have a Q, so let's put this here. Lawrence Berkeley National Laboratory. Superconducting radio frequency. These are some wonderful abbreviations. Lawrence Berkeley National Laboratory, superconducting radio frequency oscillators. They've got Q around 2 times 10 to the 10th. Huge, huge number. 2 times 10 to the 10. Is that amazing or is that amazing? I just think that's good. And that's again with the niobium 310. You have to cool the system using liquid helium. You're going for, and it's expensive. And so they would have lengthy, we would have these meetings. Are we going for 1.8 Kelvin or 2.0? You got to talk about that for weeks. Okay, that's the kind of things you have to think about when you design these large machines. It's expensive to cool it, right? It's part of your operating budget. Okay, but again, this is an extraordinarily high Q. One thing we'll show on the homework is, this is fascinating, writing the Q as a ratio of these two frequencies, right? Both the numerator and denominator have dimensions in inverse seconds. We're going to show there's an alternative. Let's see if we can squeeze that in here. Alternative. We can show that Q is equal to 2 pi times the energy in the oscillator over the energy lost. Every cycle, you have a delta E dissipation. Okay, let's put that in there as a thought bubble. This is a separate item. And again, our purpose at this point in the discussion is to talk about these results. It's logically separate to prove them. Okay, that requires some effort to prove. But notice when we first defined the Q, we talked about the ratio of this central frequency. This is a number, you read this number directly off the omega axis. That's the numerator. And the 2 beta is the full width at half max. That quotient is a Q. So large Q is good. That's a narrow resonance curve. Here's the alternative. Okay, you have this oscillator, it's oscillating. At any point, you can talk about the energy in the oscillator. That's the sum of the kinetic and potential. So imagine the so-called ring down. If you have a pendulum, for example, pendulum clock, if you remove the driving force, it's going to exponentially decay away. Right? So the mechanical energy is going to get dissipated away. But at any point in time, you can talk about the total mechanical energy, the sum of the kinetic and the potential energy. That's your energy in the oscillator. That's this numerator. The denominator is the energy lost to dissipation in one cycle. Okay, so this is, again, a dimensionless ratio. The cool way to say it is to take this factor of 2, bring the factor of 2 pi into the denominator. So then you're, rather than looking at the energy lost per cycle, you're looking at the energy lost per radian. Okay, remember 2 pi radians is one cycle. Well, we have this identification with angles, angular motion. Ultimately, you have trigonometric functions such as this cosine here, and what goes into them is an angle. So one full cycle is 2 pi radians. You can speak of the energy loss per radian. So capital Q is the ratio of the energy in the oscillator divided by the energy loss per radian. That's one way to say it. Alternatively, you can say energy loss per cycle, and you got this multiplicative factor of 2 pi out front. Okay, so we're building some experience here. We want to have a good understanding for what it means to speak of the Q. And this will be important when you take Physics 111A, for example. You're very interested in the Q, right? And we do measurements of the Q. We have electronic circuits that are oscillators, and you can look at them ring. Suppose you feed in a driving signal that's a square wave, and you can see it's very nice on the oscilloscope. You can watch the circuit ring. And when we say ring, that's again a reference to this kind of picture here. you give the system a kick, it rings down. So one speaks of ringing down. Let's put that in quotes here, ring down. That's some jargon that you'll hear in the laboratory, ring down. So let's take the opportunity. That is, you do have some dissipation, you have oscillatory behavior, and the amplitude decays away exponentially. That's the ring down. So we're gaining some experience here with this notion of the Q of the system and how that relates to this resonance feature. So it's a fascinating result that the width of this, remember this picture here at the bottom of the page is really a collection of measurements. You're in the laboratory, you have this apparatus, which we do have in room 72. You got a rotating dial. You can choose the value of omega. For every value of omega, you wait for transient behavior to decay away. You wait for the asymptotic regime. And okay, we've got an audio. We got an audio problem. Okay, it's interesting. Some people report audio problems and others do not report audio. Okay, so it looks like, yeah, thanks for the feedback, everyone. We have a situation where apparently I think one person may have had an internet problem, which could have caused the audio to get choppy. But I think the majority of people are enjoying functional audio. Okay, and again, I'm going to upload the recording, so if necessary, you can download the recording and get the audio that way. So, okay, so we have diagnosed the situation. All right, so what we want to do next is talk about the framework. Remember, these results were available to you in Physics 7a and in Physics 5a. But what we want to do here is revisit that discussion using a slightly more sophisticated framework. So here's what we're going to do. We're going to define the notion of a differential operator. Okay, so it's time for a little bit of PowerPoint overload. I'm going to put these notes here, and again, I publish these notes, right? You know, I upload the recording of the lecture. That's a video recording, and also I publish a PDF. So what we're going to do here is talk about operators. Okay. And we're going to talk about operators using the term operator exactly as it is used in quantum mechanics. Okay, so we'll have the differential operator. We have this, I'll point with a pen here. This capital D is a differential operator. You see it's the sum of three terms. Each of these three terms is also a differential operator. The first term, second order time differentiation, right? That's a differential operator. The second term, you have first order time differentiation and then multiplication by a constant. And the third term is multiplication by a constant. Each of those is a differential operator. I should say is an operator. The sum of the three operators is again an operator. Okay, so we're going to be very interested in this operator. It is a differential operator because you have first order differentiation here and second order differentiation here. Okay. We will talk about what it means to be a linear operator. So let's talk about what is an operator, and it's useful to make this comparison. We're going to use a very general term, mappings, right? And this is one of those exciting side-by-side comparisons. On the left, we have the usual notion of a function. A nice example is x of t. For one-dimensional motion, you have the position as a function of time. It's a mapping from the real numbers to the real numbers. We're ignoring units for the moment. The time axis is isomorphic to the real axis, and the position axis isomorphic to the real axis. An individual, the notation mathematicians use is this arrow with a foot. An individual value of t gets mapped like so, and a typical example is 2.5 seconds gets mapped to 3.8 meters. That's an example of a functional mapping. The differential operator, it's different. It's a mapping from a set of functions to a set of functions, okay? A typical function like x of t is a typical function. It gets mapped to a different function, okay? There's different notation here. We're going to revisit this in our next meeting, and let's look at a typical example t cubed gets mapped here to this other function. So this was a quick overview. We've reached the 2 o'clock hour now, so I'll wrap it up. But this is a quick overview of the notion of a differential operator, and we're going to revisit these topics in chapter 5. Right? All these things we've said about the oscillator with the damping and the driving force, we're going to revisit it now with the operator terminology. Okay, wonderful. So that brings us to the 2 o'clock hour. In our next meeting, we will resume. What I'm going to do now is pause the recording, and I'll stay here for a while and see if you have any questions.